Hi, everyone. Thanks for joining us today for the September virtual seminar of AI and Big Data in Finance Forum. Today, we are very, very happy to welcome Sendhil Mullainathan from University of Chicago, Booth School of Business, to tell us about machine learning as a tool for science. And then Sharad Goel from Harvard University will discuss him. There's going to be 30 minutes for the speaker and 20 minutes for the discussant, followed by questions from the audience for the last 10 minutes. So please send us your questions via the Q&A option. I will interrupt Sendhil in about minute 15 if there are clarifying questions. But any questions that involve a longer debate will be deferred to the final 10 minutes. And I want to also ask everybody to please be mindful of your questions. And finally, once the official recorded part of the seminar is over, we hope you will be able to join us and stay online for an informal short follow-up discussion. And now, Sendhil, the floor is yours. Would you like to share your slides?
Thank you very much. Let me just find the presenter button. Here we go. All right. Thank you for having me. I will dive right in. I wasn't sure how much material I can squeeze in 30 minutes. So let's see where this ends up. This is, I should give some background actually before I start. For me, one of the more interesting things about science is that I spent some time in 2012 going and asking people, what have been the biggest innovations in your field? And it's kind of interesting, the answers I got. But if you just keep collecting, you kind of realize the answers people give are wrong. And the reason they're wrong is because they tend to give you the answers that are about innovations in their field, rather than innovations in the process of innovating. And if you actually look at the history of science, the biggest changes, the things that have really accelerated scientific discovery, have not been individual discoveries, but discoveries about how we can make discoveries. And to me, that was what was most exciting about machine learning, is that it's possible that inside of it is a tool that changes how we actually discover facts about the world and change our understanding of the world. And so this is a body of work, 2 papers I'll try to get through that try to at least make concrete what that could look like. And I'm not saying that these papers are like 100% right, or this is like the way to do it, but they are more an entryway into this activity. So let me start with that. This is work that I did a while ago, and Sharad has worked on this topic, and quite a few people have as well, which is, can algorithms improve judicial decision-making? What we did there is we focused at pretrial risk judges making pretrial decisions. This is somebody comes before the judge, and the judge has to decide whether to jail them or not. And then we asked the question, could an algorithm improve on the judge's decision? Could we predict what the defendant will do and use that to come up with a better decision rule? There's lots of complexities in that people talk about, everything from fairness to econometric issues, like we don't see the outcomes of the people, whatever. But that's not what this talk is about. This talk is, we did a paper where we convinced ourselves that you can keep crime rates fixed and reduce jail populations by 40%, or that you can keep jail populations fixed and reduce crime by 24%. There's a lot of issues, as I said, including issues of whether algorithms should play a role in practice, like in what judges do. But the reason I'm bringing up this paper is, since we did that paper, the question that had been bothering us for a long time was not can, but why can judges be improved on? That is, as scientists, the policy question is, can we improve? The scientific question is, why? What are judges getting wrong? How do we go about answering this question? Well, I would say this is what all of social science is. Oh, look, people look like they're doing something wrong. Let me figure out what it is. And we have tools for this. I would come up with a hypothesis. And then we have elaborate tools for testing that hypothesis: natural experiments, field experiments, lab experiments, data sets, correlations, tons of machinery for testing. But if I went down this route, it's noteworthy that we used all this ML machinery to come up with the problem, but now we're just back to normal science. It's a little weird. It's also a little weird, the asymmetry in the scientific process, that once we have a hypothesis, the testing of it is just like, it's meticulous. The sheer amount of formalism that has gone into that over the last 200 years is astonishing. But where is all that machinery trained? Some stuff that I thought of. I was in the shower, I had a great idea. I talked to somebody who I read this thing. Remarkably asymmetric in the way we come up with the hypotheses, which we then meticulously test. So the question I first wanted to ask, and this is in joint work with Jens Ludwig, is can we formalize this process? Or more specifically, can we use ML to aid in the process of hypothesis generation? So let's do that. Let's do that for this very concrete example. How would I do that? Well, if I want to understand what the judge is doing wrong, I shouldn't be coming up with a prediction of what the defendants will do. I should turn the camera and I should predict what will the judge do. So let's do that. This is just an AUC curve of us predicting. Given everything about the defendant and the circumstance, we just throw it all into the kitchen sink and we just predict what the judge will do. And this is a sort of an AUC of 0.71. Interestingly, we can predict better what the judge will do than whether the defendant will commit a crime. It's kind of interesting. But that by itself is not, again, we haven't answered anything. What we really want to know is, what is the algorithm using to predict the judge? And is there something interesting there? So to answer that, I'm going to start with something super crude. Something to say it's crude, underline crude, boldface crude with red font is what I really should have said. It's really not that thoughtful. All I'm going to do is something that people do, often called variable importance. I'm going to take my predictor, I'm going to take inputs to it, I'm going to scramble the inputs, and I'm going to ask how much predictive power do I lose? And which input, if I were to scramble, do I lose the most predictive power? So I'm just giving you the inputs that were I to destroy them in my data, I lose predictive power for the judge. The sixth most important input is whether the defendant's current charge is a gun crime. Kind of interesting. The fifth most important input is whether the current charge is a drug crime. Fourth is felony. So you can see where it's going. It's kind of quite interesting. And in fact, Cass Sunstein has a paper where he argues that one bias judges have is towards the current charge, which even in this crude first pass, you're like, oh, maybe there's something to that, because current charge is so predictive of what the judge will do. Who knows if it's a bias, but it's super predictive. So what's the number one input? From this list, it seems like it should be some sort of current charge that's left out of this list. In fact, it turns out that the number one input is the mugshot. That the pixels in the mugshot of the defendant, not anything I did to the mugshot, these are just a raw pixel level data, is predictive. And this list is highly misleading. It's not that it's number one. It's that it's a huge fraction of the signal. It is far more important than the things below. Let me show you one way you can see that. I take the pixels and make the mugshot. I build a predictor of what the judge will do using just that. So the algorithm knows nothing about the defendant other than what's in the image. And it turns out that if you form a predictor using just the face, that reaches about 0.61, 0.62. And if you recall, since a full model is roughly 0.71, about half to 40% to half of the entire predictable signal and what the judge will do is just coming from the mugshot. Now that's crazy. But of course, it's not that crazy if you reflect on it, because there are reasons to believe that we already know that judges might be using factors that are in the mugshot. We know judges will pay attention to age. We know judges will pay attention to gender. We know judges will pay attention to race. And even more importantly, in the literature on discrimination, they'll pay attention to skin color. So we also know from the literature on psychology that there's a bunch of facial features that psychologists have already discovered. I think 4 of these that are super first order is trustworthiness, dominance, attractiveness, competence. These are called sort of like a big 4 that span the set of facial features. Maybe the algorithm is just rediscovering these things, and wouldn't be that interesting if it were, because we already know this. This isn't hypothesis generation, it's just rediscovery. Of course, the problem with this is the algorithm already rediscovering X, is that if I were to stop the Zoom right now and just say, what other X do you want me to put in there? I'm sure all of you would generate your own X, and we should just go, like, this process is almost turtles all the way down. I could just keep asking more X's. So to stop that process, what we'd love to do is we'd love to also just say, let me just deal with everything that's human intuition. So what we did there is we ran a lab experiment where we asked subjects, here's the photo, here are two photos, for example, which one is more likely to be jailed? So we captured the sum total of what people think and called the predicted human probability the final variable. We take all these variables about the mugshot, and then we ask, conditioning on these variables, is the algorithm still important? Well, the first fact is, these do matter in our data. When I condition on them, they do predict what the judge will do. That's good. We thought they should, they do. Second, the algorithm rediscovers these on its own without ever being given these features. If you condition on the algorithm's prediction, a bunch of these features either disappear or no longer matter, which means in the signal of the algorithm are these features. But finally, and most importantly, collectively, these explain very little of what the algorithm has found. There's a lot of signal left. And importantly, the only one that really captures even a noticeable fraction of what the algorithm does is gender. It's like gender matters a lot, and the algorithm finds it. But what you're left with is, say, 80% of the algorithm signal is still left and completely unexplained by these factors. I think going in, I would have thought gender and race would play a huge role, and that's going to be the bulk of what the algorithm finds. And as I said, it does find those. It finds all the signal there, but it's finding a lot more. So what is the algorithm seeing? So in one sense, this is a discovery, but it's a pretty unsatisfying one because all I've told you is there's something in the face. I don't know what it is. And it's not anything you know. Okay, great. It's something in the face that you don't know. Hardly useful. All I've done is replaced one black box, the judge's mind, with another black box, the algorithm. That seems utterly wasted effort. So what we really want is we want this thing to pop out an interpretable hypothesis. And interpretability is sort of a known hard problem. But we have tools for it. So what I want to do is to take what the algorithm sees, take what I know. So I know lots of facial features. We all know, humans know. The algorithm has a predictor from pixel space. And what we want to do is to create a communication procedure that allows the two of us to talk and produce a hypothesis that makes sense to me. So in that sense, the algorithm has discovered something, but the human has named it. And that's what we would want in an ideal communication procedure. So how can these two creatures, so to speak, communicate? The creature on the left lives in the world of functions from pixels to predictions. The creature on the right lives in the world of adjectives. Well, though they don't inhabit similar worlds or have similar languages, they do have one lingua franca, which is that they both know photos. That's the common element. I look at a photo and produce an adjective. The algorithm looks at a photo and produces a prediction. So there's sort of an intersection there that we both comprehend. And this idea that we both comprehend photos is, of course, not enough. We need to be able to talk about something about the photo. That is, it's not just a photo, but a feature of the photo or something about the photo. So for example, one of the common techniques that has been very powerful is, why don't we try to have the algorithm tell us what it's looking at in the photo? And this is the idea behind gradient methods. The idea behind gradient methods is that you take a predictor and you calculate its gradient. So at a given photo, what am I going to do? So this is a given photo. Let's zoom in. These are the pixel values. I'm going to change one of the pixel values, like red 194. And I'm going to see how much does a prediction change. Then what I'm going to do is I'm going to ask, which pixel values could I change that would induce the biggest changes in the prediction? That's a gradient method. Now the algorithm can communicate to me, can tell me, quote, where it's looking at. That's the idea behind these methods. I'd isolate the pixels that lead to big changes in predicted value. Let's see what happens when I do that. I start with this guy and I say, where is the algorithm looking? Good news, it's looking in the face. And you can do this with any image. And of course, what it gives you is the big pixel values are on the face. This really doesn't work for faces. The reason it doesn't work for faces is that what we want out is an adjective. But if you think of the adjectives like attractiveness, there's no particular place in the face where attractiveness is isolated. There's no place where trustworthiness sits. It doesn't sit on your forehead. Face features are composite functions of the entire face. And so isolating where things are going to happen doesn't really do anything for you. Great. Okay. Well, this just says we were not being creative enough. What we really want to do is, why don't we just follow the gradient? Why don't we say, yeah, you calculated a gradient, don't show where it matters, but change the image to maximally, just follow the gradient. That's all you need to do. And now you have a new image. So humans comprehend through comparison. Don't tell me where you're looking. Give me two images to compare. So great. Let's change the photo, follow the gradient to increase the probability. What happens if we do that? Well, that produces this guy, which is a hot mess. And the reason it produces this guy is kind of bizarre. So what happened? Well, if you just reflect for a minute, it should become clear what happened. When we morph the image, the reason we don't end up with a new face is we're morphing, here's the space of images, here's the contour map of the prediction function, here's my gradient, I'm following it and hoping to end up with the face. What happened? Well, this image is misleading. This is all images, every pixel combination. Faces are not common combinations of pixels. Most pixel combinations are not faces. So in fact, a set of faces is a tiny sliver of all pixel combinations. So I started here, I followed the manifold. Of course, I ended up off of the manifold of faces. So if you follow the gradient, you're not going to stay with the, why would you stay with the face? You're following the pixel gradient. So to fix this problem, what we need to do is to be able to model the face manifold and then follow the gradient to stay in that face manifold. The way we model the face manifold is we just built a mugshot GAN, where we took all our mugshots and created a synthetic model of mugshots that allows us to follow the gradient and stay within the manifold. Okay. So let's suppose we do that. So you build a mugshot specific GAN. Pre-trained GANs are not enough. You need to generate realistic mugshots. So anyway, so you pick that. These are two real mugshots, two synthetic mugshots. I actually don't know which they are. The mugshot GAN does actually an extremely good job at producing realistic looking mugshots. Once we've done that, I'm going to basically engage in the following pipeline. I'm going to take the judge predictor. I'm going to morph images left to right, low predictive probability to high predicted detention probability. I'm going to form pairs of images that I show to subjects. Subjects are going to look at them. They're going to be incentivized to guess which one is higher detention probability. They're given feedback, so there are chances to learn. And after they've done that many times, at the end, I ask them, tell me what you think mattered. And whatever they named is a hypothesis. So that's the end of the story. So can they articulate something? Well, in the first pass of this experiment, this is kind of a word cloud, and you can start to see, I don't know if you just look at it a little bit, you'll start to see there's some words really popping out. So if you tokenize it, in fact, you find that about 40% of subjects in this experiment, when asked what is it they see, they say well-groomed or some synonym of well-groomed. And in fact, it turns out, well, I'll tell you what happens with well-groomed in a second. But of course, this is no reason to stop here. Well-groomed does predict what the algorithm would say. So if we went and coded up well-groomed in a different data set, and in fact, there was meaningful communication took place. But well-groomed only explains a fraction of what the algorithm says. We can now orthogonalize against well-groomed and redo the entire procedure. And if you orthogonalize against, so now when I follow the gradient, I'm following the gradient orthogonal to well-groomed. So I'm not changing well-groomed. Interestingly, if you do that, you not only get another feature that people name, you get a feature that's stronger than well-groomed for reasons I don't quite understand. You can even see it very clearly in this photo. The feature you get is something like full-faced, heavy-faced, fat-faced. And this one's interesting in that I think most of us would have had the intuition that well-groomed leads to higher probability of release. But I think if you just introspect and say, wait, which direction does fat-faced go? You probably do have an intuition, but when I ask audiences this, they tend to go 50-50 in either direction as a collective. It turns out that being full-faced is strongly predictive of being released. So all that dieting you did is not that useful. So now, this is just a proof of concept. Do these actually predict judge behavior? Take a new data set, code these up. It turns out they not only predict judge behavior, they predict it at insane magnitudes. When I say insane to me, I don't know, maybe you don't find it crazy. It turns out things like full-faced and well-groomed are just the person holding these constant, the correlation at least, is the magnitude is around half to 2/3 of having committed a violent crime or a murder or a felony. So you can either shave or they're just the magnitudes are crazy. Are these new? Of course, you could say, look, public defenders have known this all along. So we then did a bunch of experiments with public defenders where we showed them these faces, and they certainly do not say, oh, fat face is the thing that matters. And this appears to be new in the experiments we did with public defenders and the surveys we've done with them. They even seem to work, quote, causally. Now, this isn't the paper about hypothesis generation, but we kind of did this a little bit. What I mean by causally in quotes is you can control for predicted risk. They're still predictive, but who knows? That's just a control regression. Or you can run a lab experiment where you ask subjects, which one of these people would you jail? And you give them the photo, but also all of the background information. And in that lab experiment, you experimentally manipulate well-groomed or full-faced using the GAN. And it turns out subjects, at least, respond to that experimental manipulation by increasing their jailing probability in exactly the way that the algorithm. Now, these are new subjects. We're just doing a new game. So, but again, this is a paper about hypothesis generation. Let me conclude this bit by saying, in this paper, it's not about well-groomed or full-faced. It's about a way to study people. And I hope everyone on this call has an interest in understanding humans, and not just judges or faces, but it has a few key ingredients. You just need some behavior to predict, the equivalent of who did the judge release. And you need some data with which to predict it. The important thing is you need some unstructured data. Structured data is unlikely to be fruitful because what's the room for surprise? You know all the variables in your data set. At best, the algorithm will say it's variable 18. You're like, great, I kind of thought 18 might matter. I'm glad you told me 18 matters. Unstructured data, image, language, these are amazing because they involve a lot more data than we set out to collect. When I take a photo of your face, I'm not deciding which features to code of your face. I'm just taking a photo of your face. When I collect language about you saying things, there's so much more signal there than I know about. So it's the variables we didn't think to measure. And so I think this is the recipe. If there's a behavior to predict and some rich things to predict with, I feel like this pipeline of tools that I'm describing is incredibly helpful, or can be helpful. I know I'm saying incredibly helpful. So let me move on to the next paper. In the next, which I'll do kind of quickly, the next paper deals with a scope constraint of this paper.
So Sendhil, just you have like a sense of time. You have 8 more minutes.
Perfect. Good. So the next paper deals with the scope constraint of this one. Here I was generating hypothesis, but what was our theory? Our existing theory? I don't know, age, gender, race, skin color. Our theory was some implicit understanding of faces. But there are many domains, finance including being one of them, where our theories are not implicit theories, but where we actually had explicit theories. And so the question there is, shouldn't you be doing something different, given that you can actually give the algorithm the formal theory for which you would like to understand some novel thing that the theory is getting wrong? And so to do that, what we observed is we started by saying, this is work with the Shesh Ramachan, how do theories typically evolve? For those of you who know expected utility theory, you probably learned in basic microeconomics that right after expected utility theory was created, Allais created a really quite famous paradox. I won't have time to go through it, but it's worth looking up. It's pretty interesting. it showed that expected utility theory doesn't seem to work. It's just two choices. And in one choice you choose A, and the second choice you choose B, but they're inconsistent with each other. And it's a beautifully crafted little example. After the LA paradox, some people came up with the common ratio effect. Kahneman and Tversky published their 1979 paper, which showed here's a bunch more anomalies. But they also said, given all of these anomalies, here's a theory, prospect theory. Then they said, here's some more anomalies. Then a new theory came about. The evolution of theories is through theory, anomaly, 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 theory, anomaly, anomaly, anomaly. That's not just expected utility theory. This is how game theory evolved. We had Nash. Zelton said, here's a weird game. Oh, subgame perfection. Then we had, here's a weird game, Bayesian subgame perfection. And now comes all the refinements, which you probably know about. It happens in finance. We had CAP-M. Then someone says, this is weird. Oh, that's consumption CAP-M. Oh, this is weird. 3-factor models. Oh, this is weird. 5-factor. I'm sure you guys can keep counting. I don't know what you're up to now. 25-factor models or whatever it is you're up to. But that is the evolution of every theory. And so how do we usually find anomalies? The current model of anomaly generation, and you should see this is very familiar. The current model of anomaly generation is there's a person. They look at the world. They contrast what they see in the world with what they know about the theory. They craft a particular example. That's what LA did so beautifully and said, let me show you a really minimal example of an anomaly. You've seen this in finance too. Like one of my favorite ones of these is POM 3Com. Like, oh, let me show you POM and 3Com. There should be the law of one price. Like people have been amazing at crafting these beautiful little anomalies. It's funny though, all parts of this step are human. So what I want to point out is the first step, looking at the world and finding patterns, is ideal for ML. In this work with the Shesh, what we argue is that even though algorithms can see things that we might not, that bit being potentially algorithmic still leaves this bit as human. And what we argue is that, in fact, we can make the entire pipeline algorithmic. That what we'd love to do is to build an algorithm that, given a data set, given a formal theory, like actually just given the equations of the theory or however you model the theory, can actually fully automate this entire bit. So I give you a theory, give some data, and it outputs an anomaly. And let me just give you a flavor of that, that it turns out that what's really hard about building this tool is not the places where you thought it would be hard. First, we need to formalize what a theory is. But that turns out to be hard because even though individual theories are formal, they're all formal in different ways. So I have to formalize any theory, a general model that can capture the vast array of theories. Second, you have to formalize what an anomaly is. It's a little easier, but it requires a little thinking. So we described individual ones, but notice how anomalies have nothing to do with anything you've encountered in econometrics. An anomaly is not a p-value. It's not a test statistic. It's not a goodness of fit measure. It's not even a regression. LA was just two little rows of data. You're like, isn't this funny? So what is an anomaly? And we have to do that simultaneously in a way that encompasses statistical objects like machine learning and data generating processes, because we need a tool that can mush all of this together. So we need to encompass logical objects and statistical objects, theory and anomalies with ML and DGPs. And so that, once we've done that, I'll skip ahead in the interest of time. What we're able to do is we have a tool. I'll actually show you this. What we're able to do is to create a tool that, in fact, takes a theory and outputs anomalies. And I'm just going to show you one thing, one application of that tool is back to the original LA paradox. So what we did was we took lottery choices and expected utility theory. We took our tool. And what we wanted to do was kind of do a little controlled environment test of it. So what we did is we put ourselves in the shoes of Kahneman and Tversky in 1979. So what did Kahneman and Tversky do? They looked at people's behavior and they said, I look at EU, I look at people's behavior, man, that theory is all wrong. Here's a collection of anomalies that shows its prospect theory. So they saw a world that behaved according to prospect theory and they outputted anomalies. So we took our procedure and gave it data, just lottery data, But the lottery data was from people who behaved according to prospect theory. The algorithm doesn't know prospect theory, it's just getting this data. It's given the formalism of expected utility theory and the data from a world where people behave. And we said to it, give us anomalies. Does it rewrite Kahneman-Tversky 79 is what we're asking. And in fact, first you have to ask, does a procedure produce anything at all? In fact, it does. It produces consistent lottery menus. With the exception of the lotteries not being clean round numbers, they're actually easy to interpret. Are they actually logical anomalies? Yes, they all violate EU. More importantly, they can be put into categories. We produced in this first run of the thing, we produced 109 anomalies, and they fall into these 5 categories that we created these categories. The reason we created these categories is that everything in Kahneman-Tversky and everything that comes afterwards actually only fall into these 2 categories. These 3 categories are all entirely new anomalies that are nowhere in the literature, even though they're consistent with prospect theory. And you can ask, wait, what are these things and why we've never found them? Some of these are much simpler than the ones that we have actually engineered, just in scale and size. So you could, of course, ask, these anomalies are new, but are they real? So what we did is we took subjects and we just ran them on these logical anomalies. New actual people gave them the lotteries and then said, how often did they violate EU? This is what you find. But this means nothing. Each of these are categories of anomalies. Each column is an anomaly. The violation rate is on the y-axis, but what the hell? I have no idea what a big violation rate is. So we then took the meta-analysis that are out there of all the existing anomalies, of some of the existing anomalies, and they show you in this exact experiment what the famous ones produce. So for example, the LA paradox is about here, which means these brand new discovered algorithmic anomalies are not too far from the level of violation that LA discovered in 1950, whenever. The certainty effect, another common Kahneman-Tversky one, is up here. These are lower than that, but not noticeably lower, and the common ratio effect is up here. So all by way of saying that in the first paper, I hope you took away that when we have an implicit theory, we can start to produce things that might give us intuitions and adjectives. In the second paper, I hope you get a sense when we have a formal theory, we can have procedures for the algorithm directly interacting with that theory and finding anomalies that we can then make sense of. And at least in this proof of concept, it seems to have done quite a bit on there. So let me just conclude by just sort of saying, even if you don't particularly believe these instances of these papers, I hope to have convinced you that we ought to engage much more of our time in thinking about the process of scientific discovery per se, and that ML could be potentially a very big useful tool in that activity. All right, thank you.
Thanks so much, Sendhil. So Sharad, sorry, the floor is yours.
Thanks. Okay, can folks see that? Great. So first, I just want to reiterate that I really do believe in this broader mission of using ML as a tool for science. I think there's a lot there, and I think we're really just at the tip of what it means to use these types of modern tools for reimagining scientific discovery. So that I just want to start with my interpretation of the method. I'm going to focus my comments on the first paper, and then I'll talk a little bit about the evaluation and substantive results in that particular paper. So this is my kind of take on kind of summarizing what Sendhil just described. So you have unstructured data, so you think of images, and also there's some structured data in this database, let's say, and then we have some labels here, red or blue, and the traditional ML pipeline is you're using your black box algorithm to go from this vast set of structured and unstructured data to predict these labels. So what is the goal now? The goal is to understand, to say, why is it that the algorithm is producing certain things? So we know that why questions are hard, like, traditionally you're not, it's very ambiguous to say why is a phenomenon happening. There are many answers to that type of question, but I think we have some intuition of what we're trying to do, the type of interpretation we're trying to do with these black box algorithms. And so one way to conceptualize that is you're taking your unstructured data and you're creating interpretable features. And this is a little bit different than I think what Sendhil described, but it's kind of my perspective on another way of thinking about this problem. And so we take this unstructured data and we map it to interpretable features through some process. And interpretable, this is not an entirely clear word what that means, but again, using our intuition, we're thinking about things that are interpretable to humans. And now we're going to use these interpretable features and then stick them through a white box algorithm, let's say regression. And now once we have that, we feel like we can understand maybe what's going on. And so again, the hard part here is generating these interpretable features. And so one way of thinking about hypothesis generation, as Sendhil described it, is I think of it as really fundamentally about feature generation. And so if you observe unstructured data are able to predict some decisions well, you can reasonably say, why is that the case? And why do you care about why that's the case? Maybe it's to help interventions or just kind of scientific understanding. And so now the goal here is you generate structured information, or the approach is you generate structured information, and then you fit these simple models that are more interpretable, and again, hopefully to aid interpretation. So how can we generate structured features? So one possibility, and I think this was the meat of the paper that Sendhil was talking about, is you take gradient steps and then you have human labelers, right? So you're using ML to extract structured information in a strategic way from the unstructured information, using the fact that certain that humans, maybe if you show them examples, can tell you a little bit about what they're seeing. Now, you can also say, well, there are many, many other ways to generate structured features from unstructured information, or even just without any information, without any unstructured information, there are many ways to generate structured features. So one way is just to ask a bunch of people. Give me a list of 100 things, 100 features of images that just might be useful. And you could throw that stuff into a regression. And in some ways, you're back to where you started. So now you have an interpretable set of features, you have an interpretable model, and you can see what is predictive of the final decision. So another thing that I'll kind of do here is I ask ChatGPT, what are various reasons that a judge may make bail decisions based on part of the way a defendant looks? So it gives me a long list. And in fact, the third one is presentation, defendant's grooming, attire, overall presentation. We have age assessment, maybe how a defendant looks, younger, older, but we have lots of things. And again, the point here is that in some sense, these are low dimensional spaces of features. And so almost by definition, if it's interpretable to a human, you probably can enumerate it. Now, not exactly, but I think this is the idea here, that here I said, give me 20, give me 20 things. It gave me 20 things. I think that recovered at least some of what Sendhil was finding through this alternative process. But the point to me is, if we think of this as feature generation, there are a variety of techniques for feature generation. And so one question for me is any particular technique for feature generation, in particular the gradient approach that Sendhil was talking about, is that particularly effective or useful in some contexts? And my sense is that at least in some contexts, like images, we can probably do things in a way that's more efficient. For example, just like compiling these types of lists of features. So now I want to go to the evaluation, kind of the substantive part of this paper, with the caveat that I think is Sendhil again saying the paper, and also Sendhil reiterated in the presentation, that really this is about the method, not so much about the particular results, but I think it's useful to at least think about the specific results so we can understand the method. And so this was kind of this is how the abstract is framed. We began with a striking fact: defendant's face alone matters greatly for the judge's jailing decision. In fact, an algorithm given only a pixel of the defendant's mugshots accounts for up to half of the predictable variation. So this is a pretty striking claim, and I have to admit, I was quite confused by it when I saw it, because it feels like I've worked in this space, and it seems like it seems like it shouldn't be true. So I'm going to actually argue that is probably not quite true as stated, and we're gonna go through it and try to understand where is this coming from, and why is it that this is probably not this particular statement is probably not supported by the evidence. So let's kind of look at it. Where is this, just like numerically, where is this statement coming from? So as far as I can tell, this kind of 50% is coming from something like looking at the AUC, and you look at the full model and you compare it to a face-only model. And if you do that, you have this kind of, depending, again, this is a little bit of a, it's a tricky exercise. There's not a standard metric for understanding the amount of information in these types of models. But you look at the full model and you say, okay, well, the amount of information is from 50%. This is AUC, so that's like the no information condition, all the way to 78%. And so that's your kind of 28 total information. And then you have the face only model, and you have this 13% information base. So you have about 50%. So I think just mechanically, this is where the statement is coming from in the abstract. And there are many ways to compute this. If you compute R squared as opposed to AUC, you get a different answer. And this, again, this is offered in the paper. So I think that, that this is sort of presented clearly. But the point here is that there are many different ways to even interpret this number. It's like interpret the amount of information. If I do another reasonable thing, I get half as much information, quote unquote information, than if I were to take the kind of nominal AUC. But I actually think there's a much more serious issue with this kind of measure of information. And so what is really being captured here is the fact that there's information in one's face that's predictive. But the claim, remember, is something of the effect that the face matters. And this is tricky because I would say if you're going to try to make an argument that something matters, you probably want to look at the marginal information, conditional on everything else. And so this is one way, again, of thinking about how any particular piece of information matters. You look at the marginal information. And the idea is that there's probably a lot of information that's encoded in the face that's also encoded in structured information. And so what is one way that I would advocate for measuring that type of marginal information is you look at the information in the full model, you subtract off the information in the model with everything but the face, and then you look at the full model itself, and then you divide by the full. Again, this is just some statistic that I would say would capture the marginal information of face. And my guess is the marginal information is actually quite small. My guess is it's probably an order of magnitude smaller than what you would see if you do it the other way because of this double encoding. And so let me try to explain. I'll try to explain where this is coming from and why I think it's relevant. And so again, the core issue, I think, is that it's difficult to estimate or to even enumerate the cause of an effect. And so if we see that faces are to some extent predictive of decisions, that might well be true, but there might be other things that are equally predictive or are also encoding that same information. So if I tell you that there are these two pieces of information, the structured information and also the information in the face that are both predictive, it's hard to say rigorously. It's even hard to understand exactly what it means to say if either of those matter, or in what sense either of those matter for judicial decisions. And so again, this is really coming from this mantra. It's hard to say what a cause of an effect is. Really, we should be looking at effects of causes. And so again, this is something that I really did like in the paper, is that Sendhil and Gens went beyond this and say, okay, well, here are a set of hypotheses. So now let's try to look at the effects of these causes. And so the causes are something like grooming or full-facedness. And so if you do that, so there's a lab experiment just that has shown these pairs of individuals. Unless they which pair they would detain, the authors randomly alter these faces to isolate the causal effects of one's appearances on decision. So this is kind of, very much switching from the cause of an effect to the effect of a cause, which I think it puts us back into this causal inference world. And what they do and what they report is that the experiments are more likely to detain defendants who are less heavy faced or well-groomed, even though they were randomly assigned. So we were trying to, again, isolate the effect of these particular manipulations on decisions. But if you kind of look at this a little bit more, and so here's something from the appendix, the magnitude of the effect was about 1.3 percentage points for being well-groomed and about 1.9 percentage points for being heavy-faced. And in fact, even if you looked at if the well-groomed, even that effect was not statistically significant. And so again, this sort of suggests that these effects are in some sense quite small and not even kind of accurately or not kind of confidently measured in this type of experiment. And so again, I do believe that there's likely some effect here, but I think the magnitude is relatively small. And also I want to say that these images, where are they coming from? The pairs that are being shown are from the very top and the very bottom of the distribution of altered images. So my sense from the paper is I think these are 4 standard deviations apart. And so that's like quite extreme. So we're looking at extreme well-groomed and not well-groomed folks and seeing what is the effect of that. And so likely if we were to translate this to the real world, we would see attenuated effects. And so it's just something to keep in mind. The last comment I want to make, which I think is, it got me thinking a lot about the paper. And I don't have a lot of, I'm not quite sure how to think about it. So I'll just sort of raise this question, is that there's this big question of, are judges right? And there's these kind of 2 quotes from the paper that stuck out to me. So the first is, we're not claiming that mugshots predicts, that the mugshot predicts defendant behavior. That would be the long discredited field of phrenology. And then this question, are judges right to use face information? So there's a little bit of distance between these. I understand where this is coming from, but in some sense, we very much expect the mugshot to predict behavior, for the trivial reason that the mugshot contains a lot of quote unquote legitimate risk relevant information, like age and gender. And so there's almost certainly at least some information there in that mugshot. And so now the question, which I think is the hard one to answer, is to what extent is it legitimate to use this information that's coded in the face? And one answer, again, I think you could say is basically nothing beyond what we have in the structured information should be used from the face. I think that's a reasonable answer for kind of deontological reasons, for due process reasons. We want these things to be blind from just, to encourage trust in the system. We want these decisions to be blind to the way somebody looks. I think that's a reasonable answer. But another version of this question is, what statistical information is in one's face? And that's pretty hard, or at least I had trouble trying to make this rigorous, what this question even means. And one version of it is it seems very hard to figure out to what extent or in what ways are judges accurately using information, risk-relevant information from one's face, while still making all of the usual errors that they make in their judgment. And so this is a little bit of a version of the Anna Karenina problem that, happy families are all alike, every unhappy family is unhappy in its own way. And we're saying that, in some ways it's easier to characterize what it means to be right, to use risk-relevant information. It's much harder to say, what does it mean for a judge to be wrong in a very specific way? So wrong in the sense of using their, of using information in a mugshot that is not risk relevant, while simultaneously making all the usual errors that we know that judges are making. And so this is just, I think it's a hard question, but it got me to think a bit about how can we, is it even possible to isolate these types of errors in that sense? Okay, so I just want to recap. So I think, at least one way that I view this procedure is a way to generate features. And it would be good, I think, to understand the extent to which the proposed method improves upon alternatives, like simply asking people or machines to produce a list. And the difference is we don't ask them afterwards to produce exactly the same things that the machine may have found through kind of an algorithmic method. The point is to say, generate a long list of possibilities, then throw it into your regression or whatever else interpretable model you're going to use, and then see what pops out. So again, it's a thing that one could do. I do believe that at least in some contexts, these very simple methods are probably not going to perform well. So I think it's at least just in some contexts they might perform well. And then the second is this kind of substantive claim that I am pushing back on this kind of abstract level claim of the defendant's face alone matters greatly for the judge's jailing decision. So my read of the paper is that this is largely an artifact of the statistical measure, in that I think it is true that the face encodes some information that's predictive of decisions, but it also seems likely that much of that information is encoded in structured information, or at least there's not a lot of evidence to suggest that that's not the case. And based on the lab experiments, it does seem that the faces actually have very little impact on decisions beyond the structured information, at least if we look at things like, well-groomed and full-faced, which were the experiments that were done in the paper. So in some sense, I'm actually very happy about this result, in that it's like the world is maybe more sane than I was originally thought, and that judges are actually not, potentially as kind of terrible at making these decisions than we might think. But it does, I think it adds some nuance, at least to the paper. But I want to end on the note of saying is that this, like the author is saying, and I kind of fully believe that this is really not about a specific result. It's about this kind of much more general project of thinking through how new methodological advances, particularly in ML and AI, can be used to advance science. And I am very much on board with that project. I think there's a lot to learn there, and I very much appreciate this is one particular step in that direction. So I'll end with that.
Okay, thanks so much, Sharad, for staying so on time. I was gonna tell you, if you want to do the second paper too, you have just we can go 3 minutes over, but so you're done. So thanks so much. So we have a few questions in the Q&A that I would like to ask everybody and remind them that if you have questions, please either use the Q&A option or raise your hands. So before I relay the questions to you and call on the people to ask their questions, Sendhil, would you like to answer some of, take a couple of minutes to respond to some of the note that Sharad raised?
Yeah, sure. I'm trying to think. Yeah, I think the one thing that I'm a little confused about is why you think that if we did the measure in the other direction, it would be much smaller, because that's in the paper where we, if I can find it. Yeah, here we have the algorithm on column 6 with everything. That's 0.037 R squared.
Yeah.
Then we just remove the face thing, and we get 0.0162. So we go from the other direction where we include everything and remove. And it, I mean, so
maybe I missed this, but my sense is that things like criminal history, charge information is not included here. Is that right?
In this one, what we do here, which is we have the full detained prediction here. And however you do it, that doesn't change anything. Here's a different way of saying it. You seem to have a strong view that the face is very correlated with criminal history, because that's the only way that your effect could arise. And while it's true the face is a little correlated with criminal history, it's just not that correlated with criminal history.
I guess maybe I'm still kind of confused that algo detained. So that one includes everything. Is that what that feature is?
So the controlled condition where we've included everything is where we've also included all the predicted risk and all of the whatever. The algo detain is the one that just includes the face. So we've done things where you condition for everything, include the face, or remove the face. A different way of saying it is the comparison whether you start at nothing and add face, or you start at everything and delete face. The only reason those two things can be different is if you believe face is very correlated with the everything. And in this case,
yeah. So I guess I'm very well may have missed this in the paper. So please point me to it. So I am suggesting, again, maybe you've done this, is look at the prediction with everything, including criminal history, charge information, all this stuff, and then see what is the marginal, except for face, and then look what is the marginal performance.
Absolutely.
And my sense is that the main measure that was reported at 25%, 50% does not do that.
Absolutely, yeah. Yeah, the one I reported in this, the main thing doesn't, but we've absolutely done that.
Okay, and I'm curious what the order of magnitude is.
It's the same thing.
And so the reason I'm surprised by that, although comforted for the paper, I guess, is that if you look at manipulations of the experiment, looking at things like well-groomed, like actual features in the face, it seems like the lab experiments suggest that effect is very small.
Oh, those are individual specific features.
Yeah.
That have come out of the face. Even those features don't explain a huge fraction of what the algorithm has found. And on top of it, this is just a little lab experiment with getting any movement. 2 percentage points change in a lab experiment is pretty big. Look at the percentage point change in actual detention probabilities of criminal history. Like the ranges are all relatively low. So 2%, you can make it look small, or you could say 2% is a big change because that's what. So at some level, the simplest way to think of your question is, do you believe facial features correlate with criminal history? Your point about doubly coded is exactly right. If they correlate with criminal history, then if I add faces to nothing, it'll look really big because I'm also picking up criminal history. If you don't believe it's correlated with criminal history, then it doesn't matter where I do it. And to a first approximation in this data, it's only a little correlated with criminal history. And if I'm being honest, I'm very wary of that little correlation with criminal history because that strikes me as the bias in arrest decisions, etc. So I'm just saying that I wouldn't. That's in the paper, and that certainly isn't something I would use.
And so I definitely, I am also wary, but I'm also, I'm trying to understand this 50%. And so the 50% in the abstract, it seems very, very big to me. And but so big, in fact, that I am skeptical that, as stated.
You're right to be skeptical. Totally.
And so just mechanically, the way that it was computed, if you change, you're showing the ratio of the extra AUC divided by the full AUC, just mechanically, if you're to do the thing that I suggest, it almost certainly should shrink.
Oh, it does shrink, yes.
Yeah,
but
and so
right.
And so I'm guessing, maybe let's say it's not 50%, it's something like 15%. And again, I don't know what it is. I'm just like, I didn't see that number wasn't readily apparent to me in the paper, and I completely trust that you did it. It's a very natural thing to do, but I think that to me actually qualitatively changes the interpretation.
Yeah, I'll look up the exact number. It's closer to that 25%. It's of that, whatever magnitude you decide, it's in that magnitude. And I'll be honest with you, if it's 25% of the facial, that's crazy to me.
Oh yeah.
So I don't. We're disputing a weird thing here, which is all 10%. I find that weird.
I call me old-fashioned, but I do think numbers matter. So I think the claim that 50% is
put it at 25%. Yeah. But there's a range.
Yeah, 25%. No, again, I'm being a little bit facetious, but I do think this matters. And I think, the other thing that I think it is somewhat, I would reframe the paper in the sense that if the claim, which I think is the one that's in the paper, is that something like well-groomedness has a big effect on decisions, which I read that in the paper, and I heard you saying that in the presentation, that seems to me unsupported by the evidence in the paper. Now, in the minimal sense of it's not even statistically significant.
I think I was trying to be careful about that. I'm not saying there's a causal effect of well-groomed. I'm saying is well-groomed predictive of judges' behavior, and that is very predictive of judges' behavior.
Yeah. So again, I understand we're, in some ways, this is the reason I'm pushing back on this. This is the type of paper that gets a lot of the media attention, and I do think it is important in this field, in this topic, that we are extraordinarily careful about the way this is expressed.
I'll give an example. Race predicts judge behavior. Yeah. We can't say race is causal in judge behavior because we can't experimentally manipulate race. Yeah. That doesn't make us uninterested in the fact that race.
Sure. But groomedness, you were experimentally manipulating.
No. In a little lab experiment with just because people want to see something causal in a paper. Like it's like, how are you going to experimentally manipulate in the world full-facedness?
Yeah.
These are not.
You can let me eat everything I want for the
exactly. Right.
I would volunteer for that, I think.
There you go. Exactly.
No, but I just want to reiterate that I do think this larger project is very important. Is one that I've been thinking about a lot. Is the ways that we can use machine learning to drive, revolutions in science. And I think that this is really something I wish more people were doing, and the world is moving very quickly. And so I appreciate these kind of two papers that are on the bleeding edge of what is possible with this larger project that I hope more people will undertake.
All right. This was like the best discussion ever that we've had in a very, very long while in the webinar. So thanks so much, Sendhil and Sharad. But because we are like basically almost out of the official time of the webinar, let me just briefly tell everybody that next week we are gonna have Antoinette Shore, who's gonna tell us about our crypto difference, and we hope to see all of you there. And I want to thank everybody who joined us, and specifically Sendhil and Sharad, and give them all a virtual round of applause. And so now we are gonna stop the recording, And we're going to also upgrade all the remaining participants to panelist status. And we hope that you can stay with us for a couple more minutes. There are a million questions on Q&A, Sendhil, and people raising their hands. And I have questions, Markus have questions. So we would love it if everybody else can join us. And thanks so much, Sendhil and Sharad, for the beautiful discussion.